Well, welcome to Mom. I'm Ron. I should have my mom come and do a video. That'd be Ron's mom video. Okay, so today we're going to talk about torsion. In particular, torsion is a loading. But once we identify what the loading is, then we'll talk about torsional stress. So if I take a shaft, and if we look in from this end of the shaft, what we see is a solid circle. And I take that shaft and I connect it, fix it to a wall. Now what I'm going to do is I am going to twist that shaft. And so I'm going to draw the twist as a torque. So I've just basically grabbed onto the shaft and twisted it, and the shaft wants to rotate. In this case, I'm grabbing it right at the end, and I'm twisting it. So if we looked in at the end, we would see this rotation wanting to go like that. Well, when we twist in this manner, it applies a torsional loading, that's what it is, and there is a stress applied to the shaft. And this stress is parallel to the cross section. So if you can do this if you have a piece of chalk. In the old days we had this thing called chalk. And if you take chalk and you just twist it really hard, it will twist and fail. And what you would see is basically a twisted, you could actually see the grains of the chalk twist until they broke. But that failure is definitely parallel to the cross section. So the question is then, how would you calculate the stress at a particular point? What would you need to know to calculate the stress for that point? Well, a couple of things. First of all, as I said, it's parallel, so the stress is a shear stress. And if you go up and down this shaft, the torque would be everywhere the same. Say I put some number on there of foot-pounds, maybe 100. Well, if you sum the moments along about this axial shaft, this shaft right here, whatever that torque is would be the same torque down here at the fixed end, and it would be the same everywhere in between. We will take a look at some examples where the torque is different at different places. Here, I'll draw a quick picture. If we had a shaft that had a variety of different loadings, 10 foot-pounds, 5 foot-pounds, 20 foot-pounds. Then at each location between these you would have a different torque. And the shear stress matters, or rather depends on the torque. So in this case, the torque would be, I'm just going to use the symbol T, but the torque at this point would be everywhere the same. Everywhere in that cross section, the torque is the same. Everywhere at this cross section, the torque is the same. So for a given cross section, the torque is a constant. The next thing that the shear stress depends on is location in the cross section. And we use the symbol rho for distance from the center. So rho is distance from the center. So in the center of a cross section, rho is 0. So the shear stress is 0. At the radius, rho is the radius, so we could go tau equals T times the radius. And maybe we're 1 inch or 2 inches or 6 feet or whatever. As you go from the center towards the outer edge, the rho increases, the distance from the center increases, and the shear stress increases. Therefore, we can just from this alone say that shear stress is maximum at outer edge and shear stress equals 0 at the center. There's one more term in the shear stress equation, and that is the moment of inertia. It's the area moment of inertia about the axis that comes out of the cross section. So when we were looking at beams that were being bent, we looked at the moment of inertia about the x-axis. These were beams in bending. So we're looking at what is the tendency or the resistance of this shape to resist deflection or stress about the x-axis. Well, if we let, for example, this be the z-axis, the axis that comes out of the shaft, there is a resistance to deflection or resistance to torque that is dependent on that shape, and it's the moment of inertia. But when it's, let me just take a look at this circle. I'm going to just draw a circle here. You know, if we were talking about moment of inertia about the x-axis, we would use I. If we were talking about moment of inertia about the y-axis, we would also use Ix, Iy. If this is the x-axis and this is the y-axis. But for torsion, we're not talking about a torque about the x-axis or about the y-axis. We're talking a torque about the z-axis, the axis that comes out of the paper. You wrap your thumb around there, you've got a little right-hand rule going on. So we're looking for what is the moment of inertia about the z-axis. It has its own name. It is, and its own symbol. It is the polar moment of inertia. So I'm going to grab my book. And I'm going to look in the inside front cover. We've got some, oh geez, what are these called? Fundamental Equations of Mechanics of Materials. And there's axial loading. And what do we see? Oh, sigma equals P over A, delta equals PL over AE. There's that thermal expansion, alpha delta T over L. That's all the stuff we've covered. And then down here we've got bending, and we've got My over I, and we've got shear stress, VQ over IT. We've got all sorts of neat stuff going on here. Oh, and here's torsion. And in torsion, the shear stress is T rho over J, where J is the polar moment of inertia, and here's the equation for it. If it's a solid cross-section, it's pi over 2 c to the 4th. And c is the symbol that we use for radius in mechanics and materials. So J equals pi over 2 c to the 4th, where c is the radius. And there it is. the equation for shear stress. Torque, distance from the center, over polar moment of inertia. And that's really all I intended to cover today. In our next torsional video, we will ask the question, if I looked at the cross-section and drew a line straight up and down before I applied the torque, after I applied the torque, what would that line look like? We would see that it had moved, and we call that angle that it moves through the angle of twist. That's up next. Have a nice day. Have a happy day.